Okay, you guys, we are back with part two in our first section on series. So we're being introduced to what a series is. We saw that in the last video. It's the sum of the terms of a sequence. We looked at how to find the sum of the infinite series, thinking of it as the limit of the sequence created by the partial sums. And that is kind of the large scale approach that we're going to look at everything for the next several sections and for your test that's on chapter 11. Turns out that I don't do the entire chapter 11. It's quite a long chapter, and there's kind of a turning point. I forget exactly how many sections there are where you're just analyzing different types of series. But that's what we're going to do for the first test, and then the last couple of sections are actually going to spill over to the test following. And so anyway, just kind of give you a scheme of how this is all going to work. So in part two here right now, we're going to look at three specific types of series. Actually, in this video, we're only going to look at the geometric series. I'm going to save the other ones for other videos because it would just get too long. But okay, so we know what a series is. We know the general approach to finding the sum of the series, whether it converges or diverges. So now we're going to look at specifics. So our first one up, the geometric series, and this is something that you would have seen in an algebra class. So maybe this looks familiar still, which is nice. So it always takes this form. The sum from n equals 0 to infinity. A geometric series always begins at 0. And it looks like a times r to the n power. A is a constant. The r, it stands for ratio. That's raised to the n power. So where do we get that name, that word ratio? Well, if you thought about the first several terms, well, if we raise it to the 0 power, it would just give us a to the first power, n equals 1, to the second power, right, n equals 2. So every time we're multiplying by r to get the next term. So the ratio between terms is r, you might say. One thing to keep in mind, a can never equal 0. That wouldn't be a very interesting series. They'd all just be 0. So, okay, the geometric series. So let's look at a couple of... Oh, actually, before we get to examples, we're going to have... we're going to see the geometric series test. Okay, this is great. So somebody already went through the trouble of thinking about every type of geometric series and when it would converge and when it would diverge. Well, if your common ratio r is greater than or equal to 1, it probably doesn't take a whole lot to realize that that sequence would diverge. Let me pull that back out, so might as well do it like this. Yeah, so if your r is bigger than or equal to 1, those terms are going to add up to infinity. But if your r is less than 1, it will always converge when you add all the terms together. In fact, we even know what it will converge to. The sum of all infinitely many terms will be a divided by 1 minus r. Again, that's something that you would have seen in algebra when you studied sequences and series. We're not going to prove that formula. That is what it is. So it turns out this is pretty unique. Usually, we're not going to be able to figure out what the series actually adds up to, just whether it converges or diverges. Geometric series is special. Not only would we know what it converges, there's a very simple formula for what it actually adds up to as well. So it's kind of course, the first one we learn is the unusual one, right? That's the way it goes. Okay, so now let's get into it. The question is, Does the series converge or diverge? And if it converges, to what? Okay, we can do that. Zoom out a little bit here. So let's look at this. Sum from n equals 0 to infinity, 3 times 6 over 7 to the n. All right, well, I could probably say, hey, trying to figure this one out, on your own in the next 60 seconds. Turns out this fits the geometric series perfectly, right? R3 is A, 6 over 7 is R. We can recognize those values. Okay, well, does it converge or diverge is the first question. 6 over 7 is less than 1. So we know, or the absolute value even, that's important, it's less than 1. So we'll know that this converges. And if it converges, we'd like to know to what. And okay, no big deal. Let's just give away the whole thing. The sum, S, 3 over 1 minus 6 over 7. And if you crunch that out, you'll quickly find that that's equal to 21. So the series converges to 21. And we don't just stop there with our answer. We say it converges to 21 by the geometric series. Or you might even see, probably what I should have written is, by the geometric series test. Kind of we're citing our test back here. We're nowhere in this case, converges to that. Okay, why is that a big deal? Why am I citing the test? Well, we're going to learn a lot of different tests. I believe we learn 10, possibly 11 tests in the next several sections. And so not only do you want to say if it converges or diverges, but you want to say by which test you applied. So here, converges to 21 by the geo series test. Okay. Let's look at, so yeah, there's my note. Cite the test. So let's look at the next one. And I wanted to kind of compare these two. So this one's, if you understood the last one, this one's pretty much the same. I just put a negative sign in there with the 6 over 7. Okay, so we can recognize this one too immediately as a geometric series. Our A is 3, but now our R is negative 6 over 7. So okay, so we know it converges. The one thing that will change is what it actually converges to. And so I've got some notes there on the side. I'll just kind of show you this. We put in the A and the 1 minus R, and we simplify that. It turns out this time it's 21 over 13. So this series converges to 21 over 13 by the geometric series test. Okay, interesting. Maybe let's try and pause and think about that. So the previous one to 21, this one to 21 over 13. And instead of just kind of well, that's what the formula said, so I'm not going to think about it too much. I'm just going to move on. What's that actually mean? This will be helpful just conceptually what's happening. So in part A, the comparison here, in part A, this is what was going on with the individual terms, right? So the first term at n equals 0 was 3. The second term would have decreased a little bit because we multiplied by 6 over 7. And then they go down, down. We keep multiplying by 6 over 7. The terms are closing in on 0. Of course, we're thinking of adding all of these up. So when we add all those infinitely many terms together, think of it like stacking up. Every time we add another term, it gets closer to 21. Whereas in part B, the first term was still 3, but then the second term had a negative. We multiplied by negative 6 over 7. Then a negative again. So the absolute values were the same, but now they're jumping back and forth over the n-axis, going back and forth between positive and negative. Well, think about adding these together. If I take a positive and I add a negative, well, now it's just the tiny difference between them. Whereas back here, if they're both positive, then I'm always stacking up, up, up. It's always getting bigger, bigger, bigger. But here, as I subtract, now it dropped dramatically, and then I'm going to add on this positive bit, and it's going to be this, just these tiny differences when you actually go to add these positive and negative numbers. There's so much that cancels, instead of it just stacking up, each one bigger than the next. This series has a monotonic behavior, right? It's monotonically increasing. Where here, you're kind of like doing this back and forth thing around 0, and it's the sum is going to be much smaller. Okay, I think you get the point. Just wanted to illustrate that. Let's move on. I just have one more for us to look at here with geometric series. See if I can fit it in without giving it away. We don't need that theorem there at the bottom. All right, here we go. So they'll throw some curveballs at us, right? Geometric series, pretty simple. N equals 0 to infinity. This time it's 1 over 2 to the n. Oh, that looks familiar. Plus 6 times 5 to the n. Like, oh, wow, I'm not sure. But it turns out, right, this by itself is a geometric series. This is a different geometric series. So what we can do is take the sum from n equals 0 to infinity of them separately. So I'll take this sum, I'll add it with that. And I still don't know if it converges or diverges, but now I've got something to work with. Okay. So hopefully, again, I'd recommend you guys are writing all this down. I'm probably going way too fast. Luckily, it's on video. Okay, so where would we go from here? Well, probably, this first one we need to write that a bit differently to recognize how it's a geometric series. 1 over 2 to the n. That was actually way back from the first video at the beginning of this section. I want to think of that as 1/2 to the n. Makes sense. 1 to the n is 1, so okay. The other one I don't need to change. And then I can recognize, hey, here what my a is 1, my r is 1/2. Well, if my r is 1/2, that will converge. That's great. But on the other side, I've got a 5 as my r. Well, that's bigger than 1. That diverges. So what would we say about the combination of the two when we add them? If one converges and one diverges, then the sum is going to, oh yeah, cite your test by GeoSeries. Then we know the sum is going to diverge. If you take a number and infinity, right, then the infinity's going to win in that case. So this diverges by the geometric series test. So some cleverness here. They've kind of mixed things up a little bit, and we had to rewrite that one. Then we had to use that logic there, but hopefully that makes sense. You guys follow all of that. This is the end of our conversation for now on the geometric series.